When working with complex, heterogeneous tabular data, machine learning engineers consistently turn to tree-based ensembles. Libraries like XGBoost and LightGBM have earned their status as the definitive baselines for these environments through years of rigorous benchmarking. To evaluate these models properly, we rely on a standardized workflow. We divide our data into strict training, validation, and test sets. We build a high-contrast boundary between these splits, specifically to prevent data leakage, ensuring our models learn actual patterns rather than memorizing the answers. Yet, despite our strict adherence to data splitting, there is a statistical flaw built right into the training phase of standard gradient boosting. The algorithm inherently leaks target data into its own gradient estimates, creating a feedback loop of self-influence. Identifying and fixing this specific structural flaw was the catalyst for CatBoost. Developed at Yandex as the open-source successor to their proprietary MatrixNet system, it was engineered from first principles to prevent this exact type of leakage. You cannot tune your way out of algorithmic self-influence with hyperparameters. Resolving it requires a structural redesign of the boosting pipeline itself. To understand why, we have to look closely at the math. Look at this excerpt defining the conditional distribution mismatch. Specifically, focus on the loss gradient equation at the top. This is the formal mathematical definition of a concept called prediction shift. Notice what happens here. To compute the loss gradient for row I at iteration t, the formula requires the prior model state. The model evaluates its own previous predictions on the exact same training data. Because that previous model was trained using the target label yi, the conditional distribution of the training point is skewed. It does not match the conditional distribution you would get from a fresh, unseen test point, drawn from the exact same data. Operationally, this means your algorithm is spending its iterations chasing biased residuals. It is optimizing against a distorted target, rather than true out-of-sample gradients. This mathematical reality proves that any standard GBDT trained on its own residuals carries an inherent bias. To eliminate that bias, we need a mechanical intervention that prevents the algorithm from looking at a row's target while calculating its gradient. CatBoost introduces a primary algorithmic mechanism to break this feedback loop. It's called ordered boosting. Instead of processing the entire dataset simultaneously, ordered boosting creates a virtual time access. It does this by randomly permuting the training dataset, assigning a strict sequential order to every single row. This establishes a strict exclusion rule. If the algorithm needs to compute the gradient for, say, row 3, it must use a model trained exclusively on the examples that precede it in the permutation, rows 1 and 2. The target for row 3 is entirely isolated from its own gradient calculation. A perfect execution of this logic would require training a separate model for every single row. To manage the computational overhead, the practical implementation uses an efficient approximation, maintaining the temporal logic without the impossible hardware cost. By introducing virtual time, CatBoost deliberately trades away a small amount of variance on the earliest rows in the permutation. In exchange, the algorithm structurally suppresses target leakage. This leakage control extends heavily to categorical data. Standard libraries like LightGBM and XGBoost handle categories downstream during the tree-splitting phase, using optimal partitioning algorithms on sorted histograms. If your pipeline forces you to handle categories manually before they reach the model, you typically resort to one-hot encoding. With high cardinality data, this causes your feature dimensions to rapidly explode outward, diluting the predictive signal across thousands of sparse columns. CatBoost takes a different route. It natively encodes categories upstream, well before tree construction begins, utilizing a mechanism called ordered target statistics. It applies the exact same ordered permutation logic here. When calculating a statistical replacement for a category in a given row, it evaluates only the target values of the rows that preceded in virtual time, neutralizing the threat of target encoding leakage. Extending this ordered logic to the categorical encoding phase changes how the model treats high cardinality data. It transforms a messy preprocessing liability into a native architectural advantage. To understand CatBoost's tree structure, look at this excerpt detailing the foundation of pack learning. Focus on the equation where the error rate epsilon is strictly below 1/2. Boosting theory relies on base models that are weak learners, models that only need to perform slightly better than a coin flip. Because ordered boosting and native categorical statistics are mathematically complex, CatBoost makes an architectural trade-off. It offsets the heavy lifting of the algorithm by strictly limiting the capacity of these weak learners. It does this by deploying symmetric or oblivious decision trees. Unlike a greedy, leaf-wise tree that grows asymmetrically, a symmetric tree applies the identical feature split at every single node on a given depth level. This forced symmetry serves a dual purpose. First, it acts as a highly effective structural regularizer, preventing the algorithm from chasing isolated noise deep down in small, fragmented branches. Second, this uniform structure enables ultra-fast, bitwise scoring protocols. When deploying to production, inference speeds are optimized because the uniform splits allow for highly efficient cache utilization. Deliberately limiting the capacity of individual trees through these symmetric constraints is precisely how the ordered ensemble manages to generalize to unseen data without overfitting. CatBoost differs from its peers through its internal execution flow. It replaces the standard boosting routine with a pipeline engineered around leakage control. In the no-peaking pipeline, a data row undergoes quantization, then takes its place on the permutation axis. Through categorical encoding and gradient calculation, its target remains isolated, evaluated only against preceding data. Finally, tree construction executes a symmetric split. Compare this isolated, mathematically sound sequence to the standard GBDT workflow, where every row repeatedly evaluates itself across every iteration. Data splitting is a necessary protocol, but it does not protect your model during training. When operating on complex, categorically heavy tables, understanding and deploying the specific pipeline provides a rigorous defense against algorithmic self-influence.